So this next entry starts off with the Python native version that I built using a Qt UI, so things can go much faster. I got it up to about 10,000 nodes. You'll also see me start to introduce things like lateral voting and the reality token, because at this point I was starting to put together the idea of this being an active inference framework and starting to build what an end-to-end loop might look like. So let's check it out. This is the new app that I've created, which is a native app in order to run the encoder predictor memory modules much faster than the previous version. So I'm just going to get right into how this thing works. So right now we're going to be looking at the audio modality. You can see now we actually have a video input tab as well because we can accept video as well as data streams. But for now, I'm just going to do a quick refresh on how the audio stream works. So we're actually going to be starting with a synthetic debug type audio stream. I'm going to use what you can see we have a lot of new encoders now, but I'm going to be using the Cochlear biomimetic audio encoder. That's working off of 128 filter banks that are operating at the Hoff bifurcation. It's a very, very fast encoder, requires very little pre-training. So I'm just going to start. I'm going to enable monitoring so you can hear that tone, but I'm going to turn it off because it's rather obnoxious. But as soon as I hit play, it's going to go into bootstrapping mode. It's going to start, learning those features, and then it's going to start inferring. So let's go. Okay, you can see the loss dropping here. The MOC, which is the basically that auditory reflex is staying rather constant because we've got a stream of input signals that look like this. And I'm gonna stop the monitoring now so we don't have to listen to that obnoxious tone, but we can see the waveform passing through here. I'm gonna stop bootstrapping as soon as it drops. So right there. Okay, so now it's building a knowledge graph. I'll turn this back on so we can watch. Okay, so you can see the embeddings are creating a knowledge space of noise right up in this area. The two tones are using only two nodes here. And the reason they're using more than one node is because if I switch back to the waveform, we've got a 50 millisecond window of audio. That's our buffer, that's our latency. And what that means is, depending on where in the waveform it's doing the sampling at that point in time, it may use one node or another, but you can see the embeddings stay very consistent, right? So let me just describe what we see on the graph here. On the left-hand side, we can see various, the audio coming in. Now the Cochlear encoder is just taking a straight audio just straight audio samples and then turning that into embedding. So we can see the features of the layers inside of that encoder in operation. It's using a bit of a wavelet type thing. So at least you can watch how these features are being turned into the latent embeddings, which are then turning into nodes in the graph, right? Now, if we look over here, what we're looking at is the time loop error, right? So that every time the sound changes, that's when you see a spike, right? It's actually surprised by what just happened, right? It's trying to predict into the future, and it's also looking into the past to try to determine what's happening. Now, the time loop error is generated from a very tiny little perceptron. Maybe it's only two layers or one layer, depending on how sophisticated that even needs to be. It really only needs to predict a few tokens or a few segments in advance and a few segments in the past. And you can see it is being confused. It is like, oh my gosh, something's changing. Something's changing. Now, if that were those were actual surprises, you would see this threshold go up. But because they're triggering baked nodes, we have this feature here, which is called, it's part of our adaptation. So this is the suppression slider here is the amount that a baked node is influencing the surprise metric, right? So these spikes are actually getting pushed down by this suppression mechanism because it's not a surprise, right? So this is a self-regulating system. It doesn't, it's not really going to feel the surprise if something familiar happened. It's just that this time loop encoder or this time loop error generator is not a smart. It doesn't need to be smart because the smarts live elsewhere in the system, right? So the smarts are in the knowledge graph, and this is reactive. So we have very short-term reactivity and then long-term knowledge that's baked into it. So one of the other really interesting things that we've got going on right now is if we look at one of the new views that we have here, inside of advanced settings, we can see that there is a socket controller. So right now it's going to be sending streams of reality tokens to the server, and those reality tokens have very simple metrics inside. So if I bring that up here, this is just the log of what's being received right now. So you can see that we've got a stream from Amy Agma 1, which is the name of this agent ID. It's broadcasting locally. It's running, and we can see a latency. We can see dopamine is at 0.5 because it's triggering a lot of baked nodes. Now, dopamine, serotonin, we're using these terms very loosely. I know they're not exactly aligned with how they work in biology, but it's just a way for us to talk, right? So serotonin is actually generated from the blue line here, which is the TLE. And the serotonin is a transient trigger that's going to happen when you have a baked node or a super node, right? So the super nodes were the big ones that I showed you. Right now, it's not set to do that automatically. We need more real world cases to do that. But one thing that you can see here is that the path history is the main component that's being transmitted, right? So I did add those labels for 440 hertz and 1000 hertz, and all of that can be transmitted into the next abstraction up. Right. So the only thing that we're sending is the dynamics of the system here and then the path history. So you can see you can rebuild quite a lot. So these become embeddings in the next layer up. Right. So node number 26, node number 9, like all of these things, including the path the knowledge took to get there, is the pattern that's being transmitted out of this EPM module. And that's how you can start to see that, using lateral voting and creating these new embeddings, we start to build a brain that's extremely reactive to its environment, right? This is really just to sort of like seed the ideas right now of where this is going to go. I have the technical paper that describes where this can go into a real embodied intelligence system. But for now, let me just go back to the features that I have in the encoder predictor model simulator that I have right here. So for one thing, if we're looking at the total latency here, we can see that's very low, right? The latency does include this 50 milliseconds here, but these are extremely CPU efficient modules. I'm running this all on the CPU now. The only thing running on the GPU is just doing the math to display the physics of looking at the graph, right? So I actually started off with trying to run everything in a GPU, but it actually ended up being too slow. Just getting audio samples into the GPU and back was slowing things down. So actually, we just saw a node disappear. That's actually part of the brain as well. We have active decay turned on. So a node that didn't get promoted eventually died out, right? So we have that active forgetting as well if there's just noise in the system. So these are all these nodes have been baked because they've been triggered many times. So this one here has received 506 hits. These here have probably a lot more. Okay, so 400, 265, 310. So we're starting to build up a confidence in what these nodes actually mean, right? So if we bang on the same nodes over and over again, or the same patterns over again, that's representing a true concept, right? And that's what's getting transmitted up to the next layer. I'm going to go to video input. Let's see if this works. Okay, here we are. Here I am in the video preview window. So I'm going to switch back over to the controls, and we're going to do one of the new retinal encoders. So what I'm going to do is actually reset the brain. And then as soon as I hit play, it's going to start that bootstrapping procedure. And these nodes are going to disappear once we do a refresh. Okay, so you can see the latent embeddings that are happening here. And it's actually running. Like I can do a bootstrapping, right? So right now it's bootstrapping. As I move my hand, if I move around in front of the camera, you can't see that now because it's not going to show you the inside of the network. But right now it's like you can see the loss is dropping quite low. Because I have a static background, I'm moving, but I'm not taking up a huge amount of that image. We're not driving a car around or anything. So I'll stop the bootstrap. It's going to start running. And you can see the graph got cleared. I'm going to turn up the sensitivity of the tokens. And as soon as this threshold drops down, it's going to start creating new nodes. So the system does have to stabilize first. And the threshold has to get down to where the signal really is. And that's one of the really important things about this time loop error. So even though the time loop error is like way down there, it's still finding features, right? This is from the playful machine. So as I move my hand around, you can see it's creating new nodes, right? So a hand moving like this is creating nodes in the knowledge graph. If I turn my head, if I reset, one thing I was able to do before is actually have it recognize my facial features. Oh, we have to wait for the time loop error to come down. It should start making some nodes in the graph as soon as we hit that TLE that's very low. There we go. Okay, so we've got a couple nodes in there, which is basically the picture as it sits right now. But if I get very close, so you can see when I open my mouth, it goes up here and then it goes down there. So a face with its mouth open occupies that space. And so you can see like this is going to create many, many thousands of nodes, but that's fine. I've already designed the system to be robust for up to 10,000 nodes. It really doesn't even use that much memory or CPU. And now we can actually see the surprise happening here. So if I actually get out of the way of the system, I'll get out of the way of the webcam, that TLE is going to drop. It's bored, nothing's changing. And then as that threshold drops, it's going to keep dropping. And we can change those dynamics. We can make it adapt faster by changing this control up here. That might be convenient for this demo. Actually, yeah, we want to bring that down there. But essentially, we want to when things get surprising, it crosses the threshold and new nodes are created, right? And those trajectories are put into place, right? So you can see it's drawing those new nodes when motion happens and all of that. So that's the retinal one that we have, that very lightweight encoder. We have other ones, so optical flow. So right now it's going to do some training on optical flow. If I connect this to a self-driving remote vehicle or something like that, this part would be, or a drone, right? Obviously you could use this for drone applications. Optical flow is used for vision systems where they need to know if something is moving or you want to stay stationary, right? So they use optical flow to keep drones in one place or know how fast they're going. Okay, so you can see the optical flow happening here. If I stay very still, it goes black, but if I move my hand on one side, you can see the flows happening there. If I move my hand on the other side, basically this is how insects see. They see an optical flow, right? So that's one way. We also have a few other different methods for video. Let's see, salience. So this one I think I need to tweak a little bit. It looks like the thresholding for the contrast that's created by the saliency one is not quite right. More tweaks to make. Ventral. This has to do with colors. I'm going to do that. I'm going to test this one some more. So what I've done is I've created a bunch of these video type encoders. I'm not as familiar with video as I am with audio. So these are all going to be very experimental and just see what happens when you run them all together. So the fact that I have, okay, so here we go. This is doing a little bit more with the, this has color information, even though obviously this, the internal structure that I'm displaying here is in black and white. So yeah, you can see how you can create an EPM, these encoder predictor memory modules using any type of sensor input. And we can also see right here that, like, look, I'm using video and we still have the same type of output. When it says new concept, that means a new node's been created. So that'll be important for the voting to take that into consideration. If it gets a new concept, probably wants to ignore that at first. It's going to get downvoted because it's not something that's very, I guess we could say, if a new node's been created, you really want to know that's noise. But then, who knows? Like, we could turn that, it is going to have that big, serotonin drop, right? When something new is happening, so those dynamics really, really matter. So we've got to, I've got to look into some of these things here, like why is the serotonin staying fixed when I'm in video mode? A few little tweaks I'm going to be making, but you get the idea. It's quite robust at this point, and I can run many instances of this. So if I launch another instance, it's going to run fine on this computer. So I could do video and audio at the same time on a single PC. You could imagine running, if I have an SDK of this, like I said, all of the heavy lifting is actually in the graphics here of showing us the graph. But an SDK running in C or C++, on a Raspberry Pi, you could run multiple encoders or multiple EPM modules on a single Raspberry Pi or other type of, low-cost chip. And then we can do that lateral voting and combine these things so that it's scalable for robotics and other applications. So I know it's a lot of very interesting things happening with this system. And it's ongoing, and I'll make a new video when I have some more interesting stuff to share. Talk to you later.